So in this clip, we're going to look at the queuing models. So the first order of business in most analyses of this kind would be to get the base case sort of sized up. So I'm going to go into Canvas, and I'm going to pull up the calculator. So let's just resize this. And I'm going to use, so the details on this, let's just sketch it up just so that we are clear on what we're looking at. So it is, it's going to have to be analyzed given the tools that we have. I'm using a GGK calculator, just put that in blue. So I have for each of these people, Jivika and Shijing. Customers arrive at each of their lines at the rate of 65 per hour in a Poisson process. That's key. That allows us to use all of these. All of them require that we have a Poisson arrival process. Now, the reason that this is going to be the one that's relevant is because I have normally distributed service, or at least I'm going to assume that a service is normally distributed because there's a mean of 40 seconds and a standard deviation of 20 seconds. Those are the service times. Okay. And I'm going to convert that to a rate. So in fact, to get a rate, the rate here would be 90 per hour. Is that right? Yes. How do I get that? It'll be 3,600 seconds in an hour divided by the 40-second mean. And then, of course, the standard deviation is irrelevant, the 20 seconds. And then they leave. Okay, and that's true for both of these. Now, because they're identical, we can analyze just one of them. We're assuming that they're essentially statistically identical and independent, so it's only necessary to analyze one. So this actually, let's just clear that just a tad. It actually is an MM1, MG1 system, Poisson arrivals with rate 65. Then it has general service, and then there's one server. Okay. In our available calculators, the only one that's going to work is to do it as a GG1. Okay, and we can set it up that way. So that's our initial setup. Now, the parameters that we're going to need, we'll go in here and let me just click on this and open up our calculator. Now, sometimes when you open this up, you'll see you have to restart the space. This is an app that lives on huggingface.com. Really, it's for language models, and I'm sort of abusing the space a little bit to host this queuing calculator, but it will populate, and we will be able to punch out data in. It's in the text is a little dull, I see. So just zoom in and make it work for you. So the arrival rate is 65. Now, for an arrival process, CV sub A squared, and this is always going to be true for a Poisson process, this is equal to 1. And the rationale there is, if you take a look at the inter-arrival times in a Poisson process, the mean inter-arrival time and the standard deviation of the inter-arrival time are identical. And so this is the CV sub A squared is equal to the standard deviation divided by the mean. But since these two guys are identical, that just simplifies to 1 squared. Let's just do the CV sub P squared, this one here. So CV sub P squared is going to be the standard deviation of 20 divided by the mean, and then square that. So this is a statistic, maybe a little less familiar, but it's a scaled standard deviation essentially. So this is 20 over 40. That's 0.5 squared, 0.25. Okay, so it's just a matter of plugging these guys in and getting our answer. So this is 1. This is going to be 90 because I did that calculation previously up here, 3,600 divided by 40. This is 0.25, and I have my 1 server. Go ahead and hit submit. And we will clear, we have our output here. I just scroll down a little bit. So some of the key stuff that I need is going to be the utilization, 72.2%, not particularly heavily utilized. There'd be room to grow a little bit. It's a human server, and so getting into the 90s would become a really hard job, but something in the 80s would be tolerable, I guess. Subject to personal preference and work ethic and whatnot, but 72 certainly room to grow a little bit. And then one of the things that's going to be very important to the customer is going to be the average waiting time in the system, W sub s. And so I'm hoping we can let me just see if I can get a calculator up here. Let's just see what 0.0, let's clean that up a little bit. So let's have a look at this 0.0292. Now this will be in hours because the arrival and service rates were expressed in hours. So if you want to get it in seconds, you're going to multiply this by 3,600. So it comes back at 105 seconds. So that's less than a 2-minute wait-in system. So from the time of arrival to the time you have your drink in hand, 105 seconds. Okay, it is an airport setting, so the time is pretty critical. All right, so that's the base case. Now, let's go ahead and see what happens if we train. So the training brings an improvement of 60% in the standard deviation. So the standard deviation was originally 20 seconds. And then if we end up with 40% of the standard deviation, let's try that again. Go here. So the deviation is going to be impacting us here. CV sub p squared with the training. So it goes down to 8, right? 8 instead of 20, 60% reduction. Divided by 40, all squared. And I have written down here, so that's 0.2, and then that becomes 0.04. I think that's the only change we need. Keeping the lines separate, these two folks are sort of operating separate lives, each serving 65 per hour. Let's just go ahead and plug this in. So lower standard deviation, lower variance, it's better for the customer. Waiting times are going to drop. Let's just see by how much. Okay, so I need to slide this over. So notice how the utilization did not change. You're still at 72.2%. And then your average time in the system is now 0.0261. So let's see if we can just run that through our calculator. 0.0261 times 3,600. Try that again. 0.02. Was it 0.0262, right? 0.0261 times 3,600. So now you're down from 105 seconds to about 94 seconds. You've saved around 11 seconds by getting the training. Training could bring some additional advantages beyond, this reduction in the variance, making it more consistent. I mean, it could be that they're exposed to other juice making techniques. Quality could go up. So I'm not trying to suggest that would be the only win if you did the training. So something to think about. Right, now let's take a look at pooling the orders. So I'll just clean this up. So now what we're going to do is we're going to lump it all together. Let's try this here. And I'll annotate again. So I'm going to lump it all together. And so customers arrive now at the rate of 130 per hour. Service is still at the rate of 90 per hour. Now, if they're untrained, the standard deviation is 20 seconds, right? So that gives us a CV sub p squared of 0.25 as we calculated previously. And that's true for both of these folks. Okay, Jivica and Shijing, and then once served, the customer leaves the system. So identical parameters. And let's see if the pooling with untrained people makes a difference. So go ahead and zoom in here, make this 130. It's a Poisson process. This is a result that is presented without proof in the simulation in the queuing chapter. But it turns out that if I bring together two Poisson streams, that in fact it will be a Poisson stream with the sum of the two arrival rates. So the service rate remains the same. This guy goes back up to 0.25. Now we've got the two servers. So let's go ahead and hit submit. And I'm going to just slide across here and see. All right, so guess what? Utilization is still the same at 72%. And now I'm at 0.0189. 0.0189 times 3600. Let's try this here. 0.0189 times 3600. So now I'm down to 68 seconds. So base case 105, train them, come down to, what is it, 94. Alternatively, pool, and you got a more substantial drop down to 68. So what about if we pool and we train? That's going to be easy enough. All I'm going to now do is just go back in here and make this 0.04 because that's, sorry, 0.4. That is the standard deviation of 8 seconds rather than 20 seconds. We can go ahead and hit that, submit. You can see we're now down to 0.0176, 0.0176. Let me just press enter, 0.0176 times 3600. So that gives me another 5 seconds gain from 68 now to 63 and change. All right, so those are some of the human innovations in the process. I want to look now at if I had a juice bar, let's say I switched both humans out with juice bars, what would that look like? So now, interestingly, I can use either the GGK model. So let's just lay out for you a little picture here of what's going on. So arrivals are at the rate of 65 per hour. And now we've got a machine. This is a robot. This is a juice bot here. So standard deviation is equal to 0. And its service time, the mean service time is 50 seconds. So it's slower than either of the humans who on average knock these drinks out in 40 seconds. And so this one is serving at the rate of only 72 per hour, but there's no variation, right? It's a robot, it's automated. And that's exactly the same setup here for the other line. So I'm able to analyze switching both of them out or just one in isolation, because I think you can see where this is going to go. So here, 72 per hour, standard deviation is 0. And then, the claim is, as in the first, in the base case, all we need to analyze is one of these guys. And I could analyze this as an MG1 model, or I could use the MD1 queuing calculator. So let's go ahead and do both and see what we get. Now, I want to start with this GG1 since it's open. So to get this to go, we just make this 65. It is a Poisson process with a CV sub a squared root of 1. Service rate has to go down to 72. This becomes 0, and there's just one server. I'm analyzing one of these juice bots because the two would be statistically identical and independent, essentially. So let's go ahead and say submit. And the GGK model, you can see my utilization now bounces up to 90 and change, 90%, substantially more than the 72%. Why is it so much more? Well, because it's slower, right? So it has to work, more of the day, so to speak, to clear the arrival stream of 65 per hour. It's only able to serve at the rate of 72. It's got customers coming in at the rate of 65. It's just going to be busy a greater fraction of the day. But one of the important things is, what does the customer experience look like? So this is 0.0784. So 0.0784 times 3600. 282 seconds. That's more than 4 minutes. So I'm contrasting that with, what I had with the base case, which was 105 seconds, it looks to be substantially more. I'm going to go ahead and do this with the MD1 calculator, just as a contrast. Remember that the GGK calculator is an approximation. It relies on Kingman's formula, and it's not going to be as accurate in this particular case as the MD1. So this is actually sort of the definitive analysis for this single juice bod, the two juice bod case. So it's just building the app. I'm going to go ahead and just clear the annotations. It's a little simpler. All I need is a lambda and a mu here for the MD1 when it does populate. Just go in here. So this is 65 and this is 72. And I can run it and just see what I get. So there's the 90% and 0.784. I think very similar to what I had, but let's go ahead and just run the calculations. 0.0784. Let's try that again. 0.0784 times 3,600, 282. So very close. Okay, so there would be, if you did switch out both humans with juice bots. Now, I think one interesting possibility would be to switch out one human with a juice bot. Frees up the day, particularly for folks who have other commitments, maybe managing kids, aging parents, whatever. The juice bot may give them some flexibility, but it is distinctly worse service than what the human's providing. So what's going to happen is, and we can go in here and you can look at the number of customers in the line. The juice bot's going to have a longer line. So folks are not going to be willing to line up equally behind these two folks, and it's going to be dynamic. So the whole picture is going to shift, and you're not going to get an even split of 65 folks arriving at the juice bot and the remaining human. So for that reason, we're unable to use these basic queuing models to analyze this more complex situation where you have a juice bot and a human. And that is it as far as the analysis is concerned. And in the next clip, I'll just demonstrate doing some of this analysis using the AnyLogic model.